Hello and welcome back. So in previous video we computed now the pressure forces. So now let's focus on wall shear stresses, the forces at the wall, okay? Computed in Paraview. Previously also we computed the total force. We know that any distance solver will save that. Here we're going to do everything in Paraview. It's not that you need to do it. For those interested curious in how to do that, well, I'm going to show you the steps. It's a little bit tedious, and just to remind you, what we're going to do is now to compute this component, the viscous forces, which is equal to this. Okay, so the steps are pretty much the same as the previous one. Now we have the velocity gradient, we need it, okay, and we know how to compute it. We can do this operation using calculators and so on. And at the end of the day, this is your wall shear stresses, okay. And remember that you need to dot it here to get the x, y, z component. After you do this one, you dot it by the normal. So you need to compute the normals, volumes, so on, gradients. And recall that also you will have this normal component that you don't need it. I recall when I went down this rabbit hole, yeah, I think I was all computing this component as well, besides checking something else, how the computation is done. Yeah, I recall also there is a factor of 2 in the gradients, how it's approximated at the wall, so I'm going to show you that. But yeah, maybe these were the two reasons. Now, this component here, checking that factor of 2, which is not related to this, it's just the gradient or the finite difference or forward difference, whatever is used at the walls. And yeah, and for the sake of the glory, I just was curious how to use Paraview to do this operation. So let's do this stuff in Paraview. So here I just open the state, okay. Let me close it to show you again how to do this. And using Paraview 6, everything will work in older versions. I don't know how old, but at least in 5.13 everything works. So to load this state, that in the video description you will have everything. Now is FB forces, viscous forces, pressure, so open SV. Then here be careful also, you need to do the right location where you have the Ansys file, the one that you open, the inside file. I mentioned that inside is the fastest format that you can use with Paraview. It's very, very fast. I strongly recommend you, advise you to use that format. Paraview, OpenFont, CFX, Fluent, StarCC, and all of CFD solver safe in that format. Besides also BTK, Tech Plus, CGNS, and so on. So you will get, if you open that state to this window that we have all the steps here, we're going to reproduce everything from scratch. So I will leave this open if I get lost somewhere. I don't recall everything from the top of my head. So let me open a new one. Here, open, okay, close, open, and let me open the Ansys. This is the inside, and remember that Ansys will load everything, okay. So here you have all the variables, and then you need to extract blocks now to get surfaces, internal domain, and so on. So the first thing to do, the field filter, I want to apply a gradient on everything. So you have here the gradient filter. You use the velocity, and using the Fluent dataset, I know this is already a vector, okay, so be careful, and compute gradient with this name. And there you go. So we have the gradient in our dataset, and let's see what my pipeline, then there is an extract log here, we have fluid. Okay, so let's follow that one. We extract the fluid, okay, only the fluid. I don't want the walls, okay. It's important why I don't want the walls, because also you can go here and get the walls, okay, but I want to work on the fluid only. So I want to create as a slice there. Let me put it there. I don't know what is that warning, honestly. I need to check it out, but don't pay attention. And now also let's do another one. So remember that here in this one, what we have, you have the whole inner volume. So if you apply an extract surface, a filter here, let me go, you will extract the surface bound in that domain. Okay, so let me at a slice there and see that it's only the surfaces. Okay, so this is what you do to project all fields on the walls. Okay, so here when you have the walls, okay, something to point out that Fluent, you have the advantage that when you save in Fluent, Fluent will project the velocity at the walls, and then you will be able to compute gradients. Instead, in OpenFont, this is 0. So by using this trick here, you will project velocity. Here in extract surfaces, you will project the velocity, but also will project gradients, everything that you computed previously. So you work here to compute gradients and so on, all that, those quantities. Okay, so extract surface, let's see what else. Okay, then you compute normals here. Okay, very important, normals, surface. Okay, you get lost there, too much stuff. Surface normals, put your normals. Remember, compute cell normals. We're working in cell center. I saved my data in cell center style, and I recommend you also to save cell center type data. And to show you something here, we already saw that this previous video now, but just to remind you that something about gradients. So if I look at this slice here, link cameras, you have it there, and let's take a look. So in my left here, we're going to look at the gradients computed in Paraview, and here to my right, the gradients computed in Fluent. So I'm looking, okay, this one that if we go here will correspond to this one. Okay, so 0, 1, 2, 0. Okay, so here see that I'm looking 0. So we need to adjust the scales. So let's go, I know -5, 5 works fine. And see that there are different minimum and maximum. It's already telling you that it's computing slightly different, but at the end of the day, pretty much it's the same. Okay, so visually checking, you can see that it is very similar. Okay, so you can check all the components, and yeah, you will realize that. But what is interesting is that, let me go to now extract surfaces. So we look at those gradients, everything that we're projecting on the surfaces. So again, here, let me take a look. Left gradient in Paraview and gradient coming from Fluent. And let's use same scales. -5, 5. Apply, okay. And let me go here also, already there. And as you can see, they're different. And actually you will see that there is kind of a factor of 2, okay? So let me go here, and if I put this one 2.5, see that now they match, okay? So there is a factor of 2. This is a factor of 2 how the gradient is approximated at the wall. As I was mentioned, I think that this was one of the reasons I was verifying this. I was doing some other operations, and yeah, you have, I think, my assumption that there are some ghost cells computed that you use an external cell to approximate that gradient, the wall. That is my assumption. Please correct me if I'm wrong, or if somebody knows the exact reason also, let me know. But it's not related, because some people say that, okay, look at that, you have this 2 now, that the math here is right, okay? It is that factor of 2 that then we are taking into account later. You will see, otherwise your wall shear stresses, everything will be half, okay? But this is very interesting to look. Something also interesting to look here is that pay attention to when you structure faces, you are getting everything that is wrapping your domain, even the inlets and outlets. Instead here, you selected precisely what you want, okay? So there is another trick here, okay, that I want to show you that you can do. This is a new filter that you have in Paraview 6. So you go here, alphabetical, see that you have feature edges and feature edges regions ID. So this one will separate the regions, and here you will have a huge tip for those working in OpenFont, because this, and see that you're going to get that field, BTK regions, and it's splitting now by this angle. So remember, you make this angle smaller, you get more features. Larger, less features. So basically, this is what you are doing there. Separating by features. Each one will have a number, okay? And then you can start to filter, okay, to get that. So let me erase that one and redo it. So filter IDs, BTK regions. We have it here. And we have regions with a strange numbering. Okay, you have the numbering there. Okay, and now I can say, let me apply stress all here, and I want to get BTK region, and probably will be 0, I think, the whole pipe. Yes, and the other will be probably, I think, will be BTK probably will be 2, I think. Yeah, I was right. So you extract it, and that's all. You have all the quantities now. You can do all the post-processing, all that stuff here to make your life easier. You can select, and group, create a group, and now you group everything. And so this is a little bit advanced now, post-processing, but the issue that it is half the other, no? So remember, when you do in Paraview, you will need to multiply by 2 to get now the right value coming from the solver, okay? And my assumption is how the gradient is computed. The derivative, there is a goal cell in the middle, and you get that factor of 2 there. Okay, so hopefully it was clear, and I digress a lot. No, okay, let me go and erase all this stuff to avoid confusion. So there I show you that tip, because now you can see that you can split your geometries in Paraview. You don't need to use anymore that utility. I forgot what was the name to split, but whatever. You can do a lot of stuff in Paraview. So we have the surface here, and now let's compute wall shear stresses here. Let's do this computation. So this same stuff here. So look at that. The issue now that why we want to remove the inlets, because also you can get some gradients at the inlets when you do the integral. It will add some error. It's not that it's that much, but it will add some error. So if you can remove that, will be better. So this is OpenFont, Paraview, sorry, and this is the fields coming from Fluent. And see that in Fluent, it removed the gradients of the inlets and outlets. Okay. So here, okay, surface normals and the calculator. So I have my surface normal, and now the calculators are to compute those quantities. So I have the first calculator, which is this one. So let me go here and put it here, and let me copy the same name. And this will be like wall shear stress x component vector. Okay, so you have the I had assembling vector, so probably was that. So look at also the minus. This 2 is not the 2 for the gradient. I would put it somewhere else. That is the 2 that actually you have in the equation. Okay, have it there. So you have your gradient. So you look at that. This gradient, this quantity compute corresponds to the first row here. Okay, so just do your math and you have it there. So you assemble, you have that. So I guess this will be the, because what? Okay, I have my cell normal. Okay, it has to be cell data. So, and there you go. So now I have this component. But still, I don't have my shear stress because I need to dot it. Okay, so what I got is this one. Then you need to dot it here to get your complete component. So that will be the next step by next calculator. That I have it here. And see that I have dot product of the previous one times the normals. And you see the 2 here. So you can put it there and you can put it outside, so nothing changed, okay? So will be the same. It's commutative, that number there. Then it's cell center. And there you go. So we're going to have now the result, okay, which will correspond, if I will recall, to the X component of shear stresses. So on my left, let me put here X, okay, and let's go from minus 0.1, 0.1, cool, minus 0.1, 0.1, and cool, and there you go. You have your shear stresses, okay? Wall shear stresses. So you have the same quantities, remember. I multiply it here by 2, that correction of the gradients, otherwise you will have half, okay? So 0.1, 0.1. So this is also, this auto scaling is a new option that they added, a little bit annoying, but disabled there. And what I was telling you, that this will be twice, no, the correct one in Fluent is twice the one that you have in Paraview, but it's that correction of the gradients. So yeah, I put it here, and this one, you can put it anywhere you want, you can put it here, here also, if you don't put that one, you will get the opposite, so also, there, or you can, when you compute the totals, you minus and get the sign, the correct sign. It's up to you, okay? So there you go. So see that there are some noticeable differences. So see here that gradients are a little bit different computing, and here, well, how it's computed, because we left the surface, but you have that influence, so you get an idea that it will be slightly different what we have from Paraview, from OpenFOAM, but pretty much have to be the same. So to remove this, you can apply, the previous trick, you filter by edge and then extract that, or you can do selections. You have the filter selections, and things can get really crazy. So that is what I say, that it requires more tutorials to show you that if you don't know that you can select cells and so on. So we're preparing a nice series of tutorials advanced with Paraview. Hopefully we're going to add a lot in programmable filters also. So see here that in this intersection there are some issues as well. But in any case, there you go. So now that you have that X component, as you want to compute the other component, just follow here this operation, which actually I think I already have that step here. Okay, yeah, you have it there. So it's not that tedious, but you have it there. Everything you can put it on automatic and create your own filter. But it's interesting now that we want to compute the total force now. So we do the integral. So search, let's integrate. Okay, and you have it there. So it is cell data that we have. I want to see to send. So that is result. And here, let me do the same stuff. It is spreadsheet view, and I want to see wall shear stress data. This is that, and I want to see just this. Okay, these three components. So we're going to compare here. So this is Fluent, this is OpenFOAM. So qualitatively speaking, they are very similar, and quantitatively speaking, see that 1.48, 139. They are close. The differences, remember, stuff there, nothing that you should be afraid of, okay, or enter into panic, but you can see there that those errors are due to that. Okay, so now let's compute the Y component, and that one actually will be straightforward. I already have it there, so I just need to substitute it here. The minus, I put it there. And there you go. So this is a little bit closer, and let me go here and let me put that component also there. And same scale. Let's put okay, minus 0.1, 0.1. Apply, and there you go. Visually speaking, very similar. And let's do the same for set. We have it there, and put it there. Let me put the negative there, and here that one will be this one, and let's use same scale, 0, 1, 0, 1. Let me increase there, and there you go. You have it. Visually speaking, they're very similar. Qualitatively speaking, there are some errors, but look at that. All this stuff is coming from here, a lot of stuff from here, so nothing that you should be worried about. Okay, but that's it. That is how you compute your wall shear stresses in Paraview. It's not that you need it to do it, but if you want now to go down this rabbit hole and do this operation, that's how you do it. So now compute the pressure, add it to this, and you're going to have to total forces, and you can plot everything now in the surface. So remember, these are wall shear stresses. If you want the actual viscous forces, then you multiply this by the area. Okay, so you need to recall that we have the area multiplied by the area, and then you're going to have that plot of the viscous forces distribution, and then you can do the summation to get now the quantity, the total quantity. So yeah, this is it. Okay, quite cool. Okay, so yeah, I answer. Hopefully I addressed that answer. That for me, that question, that I found it really weird when people, how you do it in Paraview, and yeah, you have the software will give you everything, but now I get the point that you want to visualize or do some checks, and those are the steps. Okay, so these are the forces. We're not done yet. We have some other videos because we have moment. Moment is similar. Okay, so we are going to add another operator there, will be the cross operator. I don't see it here, but yeah, but it's pretty much the same. Okay, you have, so we're going to take the assumption that we take the pressure and the wall shear stresses, and then we multiply it now by the coordinates, and you get your moments and so on. So hopefully you found this useful. Okay, so we use Fluent database. Next video, let me show you the OpenFOAM database now case and compare with Fluent, but it's pretty much the same stuff. Okay, so thanks and see you next time. Bye.